Hello guys, today we're here to look at perfect squares. We're here to look at perfect squares and surds. So, perfect square. Happens. So this goes to 4 instead of 3. It means that we need to introduce more squares. Square of size 4 will give us a situation like this. Yep, almost there. Yeah, so remember, we're still on perfect squares and surds. Let me place this here so we can have a look, still have a look at what we're doing. Okay, maybe I'll outline it this way so that we can still have. So how many more cubes do you think can go? Let's have more of my yellow cubes. Yeah. So I have one more here, one more here. You have one more here. Let's outline it well. And then I need more of me yellow cubes. Yes, yes. Yep. Nicely done. And a few more. A bit more. Okay. So check this out. Well, you can see the roots. These are the roots going into the soil. The roots of the square. The roots of the square. How many roots do you have? The 4 roots, right? 1, 2, 3, 4 inside the square figure. But how many of these squared objects or cube objects do you find here? So let's count 1, 2, 3, 4. 1, 2, 3, 4. So that's 4 by 4, that's 16. If you want to check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it means that for a square of 16 smaller squares, the root will be 4. So the situation is different when you have to do find a squared root of a figure that is not a perfect square. So let's show you something that's not a perfect square. Yeah, so over here, you notice that I've placed one of the pyramids here. Now it's like I've cut a part of the square off. I just reduced the number of smaller squares or baby squares inside this big square. So can we still find the square root? So if we try to find the square root, we have a problem. This side, you realize that the roots on this side is 3 and the roots on this side is 4. So what this means is that we can't have one number for the number of these baby squares, right? For this figure, well, the figure to start with is not a square, it's a square that has been cut. So anytime you have a square that has been cut out, it is very difficult to find the square root, or it becomes more difficult to find the square root. So how many baby squares do you have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You have 15. So what we want to find is that we want to find the square root of 15. The square root of 15. Now, this is not going to give us one, it's a figure that lies between 3 and 4. The square root of 15 lies between the figure 3 and 4, because 3 by 3 gives us a square of 9, as you can see. 3 by 3 gives us a square of 9, and then 4 by 4 we are going to describe numbers that do not have a whole number root as surds. Numbers that do not have a whole number root as surds. So this means that you're going to likely get 3 point something here. Because we have 3 point something here, we do not want to use that in calculation, so we are going to represent that as square root of what? 15 without changing it. So while square root of 16 will be 4, and then the square root of 9 will be 3, you will notice the square root of 15 will be between 3 and 4, because we have reduced the figure into something that is not a square, a perfect square. So it's going to give us problems. So this is the idea of surds and why we use them. So we use surds because we do not want to use the decimals that they produce, but the decimals sometimes continue without ending. And if you use the decimals, engineers and other people who make use of these values can make errors. So they prefer to use these figures instead. So we can look at a situation where you get to add numbers like these that keep the square root or the squared weight. I call it the squared weight. So surds are simply numbers that keep the squared weight on without removing it. And we have to learn how to deal with those types of numbers. Yeah, so thank you very much for now. We'll look at simpler how to add, subtract, and multiply surds. Right. Will be 1 squared. So this is not a surd, but the squared root of 2. That is an interesting situation. So how do you form a square with just 2 of these? Very not possible. So how do you form a square with just 2 of these? This will not produce a square. If you want to force this to produce a square, the square root of 2. If you want to force this to produce a square, then you're going to get a number between 1 and 2, because this is 4, and the square root of 4, as you can see, is 2 here and 2 there. So the square root of 4 is 2 on the side. But the square root of 2 does not amount to a perfect square, so we keep it as a surd. So this becomes a surd. Then we can look at square root of 3. In other words, if we put 3 here, we can't create a square with it. If I put this here, still not a square. So this tells us that the square root of 3 will also be between the square root of 1 and the square root of 4. Because this is the square root of 4 and the answer is 2. But now this represents the square root of 3. So we do not have a partition between 1 and 2, as you can see. It's between 1 and 2. So it's a decimal. So we're going to keep this as a surd. Then we have square root of 4, as we mentioned. Now 4 will have a square root. You can see the root here. There's 2 here and 2 on the side. So the square root of this figure is 2. So this is not a surd. Yes. Sometimes surds can be compounded. For example, you can have 1 surd 2 plus another surd 2, in which case that becomes 2 surd 2s. And you can have 2 of the surd 3s plus 1 surd 3, in which case you have 1 here, so that makes 3 surd 3s. Very good. So we just looked at how to compound surds, adding surds. Now surds can also be multiplied. We can multiply surds, right? Yes. So the interesting thing about surd is if a surd multiplies itself, it will lose the weight. So you're going to get 2. So when a surd multiplies itself, it loses its surdness. Well, this is because the surd, this surd here means half. This is the root. This is how you write the root, the square root, and times another 2 with its root. This is how we write the root. It's always 1 over the figure by which the root by which we are finding. So what this means is that from indices, this is 2 half plus half, and that will give us 2 to the power 1, which is 2. So that's why a surd multiplying itself will produce a surdless number. In other words, a number without a surd. sometimes a perfect square can be inside a set. For example, the square root of 8. This has a perfect square inside. So there's a way we go about dealing with it. So what we do is, we are obviously going to write out what the factors are. 4 times 2. Then this will mean that this will be set 4 times set 2, or square root of 4 times set 2. Obviously this is a 2 because this is not a set, it's a perfect square of 4 cubes, or 4 squares. So the root is 2 times square root of 2 because it's not possible to create a perfect square with just 2 squares. So we leave it as a set. So another interesting thing is that when two sets multiply, sometimes you can have a coefficient in front of a set. For example, set 2 set 3 times 5 set 2. So what can happen here is that we multiply the numbers outside the set and then multiply the sets. So you're going to get 10 set 6. 3 multiplies 2. Both have sets. They are not the same figure, so they will not reduce to one figure. They will rather multiply each other and create. Another way to deal with this is to factorize the set out. In other words, this is common, so the set 6 will come out. And the one that is not common will come down. So you notice that set 6 is common, it's written outside, and the ones that have no common values, or the ones that have no similarity, are written in the bracket. So eventually what do you have? You have 9 set 6. So this is one way of writing, or factoring out similar sets to add up. Another thing we need to know is rationalization. So rationalization, so to deal with rationalization is the idea that we do not want to see you write something divided by a set. This should never happen. No, this should not happen. So anytime you have a figure and there's a root under in the division, the denominator, it has to be rewritten. We have to rationalize. So for example, if I have 1 on third 2, we have to change this. This is a no. Is a no. No. So the way that we deal about it is that we are going to multiply and then now notice that when two sets of the same kind multiply, they lose their weight, they lose their setness, so it becomes 2. So this is what we get. So 1 over set 2 is actually set 2 over 2. Remember this. This is rationalization. No. Why do I keep writing no like this? Okay, no, this shouldn't happen. So what you're supposed to do is, sorry about that, what you're supposed to do is multiply by 1 over 1. Now this 1 over 1, I'll take the set here. So this is set 11 over set 11. The 1 over 1 is the same as set 11 over set 11. So all I have to do is multiply this by that. And what does that give me? So to multiply that by that, realize that all I have is 7 set 3 times 11. Because they are different sets, they come under one square root. And then 2. Now notice the same set multiplying each other, the wig comes off. So finally you are going to get what? 7 set 33 over 22. So there's no set here. This is correct. The set down here is a no. So remember that very much. Yeah, so let's deal with another situation, which is 1 over set 7 plus set 5. This is also a no. There are sets here. This time they are compound, they're adding under the denominator. So the way we do this is slightly different. We use an idea called difference of two squares, but again, we have to multiply by 1, divide by 1. 1 over 1 will not change this, but we're going to transform the 1 over 1 into set 7, this time not plus, minus set 5. And then back again, set 7 minus set 5. Now we do this because the members here are the same. The only difference is the sign, this sign. And this is called the difference of two squares. It's very simple. In solving difference of two squares, you just multiply this set by this and this by this. I call it a smiley multiplication. So let's do that. So the top becomes set 7 minus set 5. And then smiley multiplication 1, smiley multiplication 2. So this is 7 minus 5. Set with the same set, they lose weight. So final answer will be set 7 minus set 5 all over 7 minus 5, which is what? 2. That's your final answer. So sometimes you can be given the decimals of a set. So we know that the square root of 5 is between the square root of 4 and the square root of 9, right? It's actually 2.236 ... You can see why we don't use sets in this form, because it will be difficult or you will be exposing yourself to errors. So we use them in this form, and when we need them, we fill them up with this form. So if I have to use this, given that set 5 is this, if I want to find 1 over set 5, like I said, this is not rationalized. So I multiply by 1, divide by 1. This turns into 5 on 5. And this becomes set 5 over wig times wig, the wig comes off. So 5 times set 5 becomes a setless number, which is 5. So all I have to do is replace the set 5 with its figure, which is this. Since we have been given, we just put 2.236 over 5, and whatever figure we get by dividing this will be our answer. Support the channel. Don't forget to support the channel by subscriptions, and as you know, we'll be there with the cubes for you to play with and learn, expand your mind.